We've been talking a lot about expressions in this unit, and we're really moving towards the understanding of using what we know about expressions to solve for unknown variables in an equation. So today we're going to be looking at our first step in this process, and that's solving one-step equations. So in order to solve an equation, the first thing that we must realize we have to do is to isolate the variable. Okay, we got to get that variable all alone and by itself. And in this, we have to keep each side of the equation balanced. And we've looked before at hanger diagrams, and that's what represents the balance when we're looking at things. So one of the key things that we need to understand is that we can use inverse operations to move terms from one side of the equation to the other, but we have to remember that what we do to one side of the equation, we also have to do to the other. So when we do this, inverse operations can be thought of as the opposite or undoing operations. So they're going to undo what one operation would do. Right, so when we think about this, the inverse or the opposite of addition is subtraction. The opposite of subtraction is addition. The opposite of multiplication is division. And the opposite of division is multiplication. So when we are looking at an equation, we can identify what operation is happening, and we're going to use the opposite operation to undo what's happening. So we want to try to get this x by itself. So we can recognize that the relationship of what is happening from here to here is multiplication. So in order to undo the multiplication, I know I'm going to use the inverse operation, which is to divide, and I'm going to divide by 4 because that's the coefficient that I have right here. When I do 4 divided by 4, it just leaves me with an x. And I could think of it as canceling out, but 4 divided by 4 is 1. But if I just leave it like that, I don't have a balanced equation anymore. If I divide by 4 on this side, I also have to divide by 4 on this side. So now I have 16 divided by 4, and therefore x is equal to 4. Looking at this next question, we can see that the operation that's happening is addition. So from here to here, we're having addition. Okay, so to undo the addition, I know that I'm going to use subtraction. So I want to get the variable all by itself. So I have to get rid of the 9. So if I use the opposite operation and subtract 9, I can get the x by itself because 9 minus 9 is going to give me 0. But I also have to subtract 9 from what's after the equal sign to balance my equation. So now I get x, and then that is going to end up equaling 4 because 13 minus 9 is 4. Looking at this one, I know that the equation that I'm going to use to isolate the variable is going to be addition because I have subtraction right here. I want to get the x all by itself. So I'm going to add 8 to both sides of my equation, right? If I have, now I have x, I'm going to bring my x down, and then a negative 8 plus 8 is 0. So as long as we recognize that that negative 8 plus 8 is 0, and then we have 14 plus 8, and 14 plus 8 is going to give me 22. Looking at number 4, my operation that I have right now is division. That's what the fraction bar here is going to mean. So in order to get the x by itself, I'm going to have to multiply. So we can put this in parentheses to represent multiplication. And I'm going to multiply by the denominator. Okay, so I'm going to multiply by this denominator. And then I have to multiply this side by the 5 as well. So when I think of this 5, and I can think of it like 5 over 1 if I wanted to, this is going to cancel this out, and I'm left with an x, and then that is going to end up equaling 65. 13 minus 5 is going to equal 65. And this one, simple and easy. I know to get the x by itself, I'm going to have to do the opposite. So I'm going to have to add the 6, and I'm going to have to add 6 to both sides so that I can keep it balanced. We think of it like that hanger diagram, trying to keep it balanced. All right, so I'm left with, I can bring my x straight down. Negative 6 plus 6 is going to be 0, so I don't have anything left with that one. And then I know that's going to end up equaling 17. My last and final one reverts back to kind of what we did in the first one. This means multiplication. So in order to undo the multiplication, I'm going to divide by the coefficient. So I'm going to divide by 2. And 2 divided by 2 is 1. So I have 1x left. And then I also have to divide this side by 2. Okay, so I divided this side by 2 and I had 1x left. And then that's going to be 88 divided by 2 is going to be 44. So one-step equations can also include rational numbers. So that means we're not always going to end up with the whole numbers like we like to see all the time. So we're going to look at some examples. Here we are going to divide by 6, and then we're dividing, remember, because we're multiplying, so that cancels out that. And then we're left with 16 over 6, which we can simplify by dividing both of these by 2. And we can get our answer of being 8 over 3. If you typed it into the calculator, you would have gotten a repeating decimal, which would have been 2 and 6, and then it would have gone on and on and on with bar notation like that. But knowing that we can stick with the fraction and be okay with that. Right, here we're going to undo the addition by subtracting 2 and 5/10, subtracting 2 and 5/10. So we're left with our x, and that's going to, remember, it's subtraction, is going to end up leaving us with just a whole 5. Now this one here, we're multiplying by 2/3. Oh, I'm wrong. We're not going to multiply by 2/3. 2/3 is multiplying the x. So I'm going to divide by 2/3, and then I'm going to take 8 and I'm going to divide it by 2/3. So 8 divided by 2/3 is going to end up equaling 8 times 3 over 2, which ends up giving us 24 over 2, which answer is led to x equaling 12. Okay, so making sure that, remember, when you divide by fractions, you have your keep, your change, and your flip. Okay, so this is where we're using all of those tools and strategies that we learned along the way to get where we needed to be. All right, this is division now. In order to get rid of that division, I'm going to multiply by that denominator, which is going to be a 3, and I'm going to multiply both sides by 3. So this 3 is going to cancel that one out, and then x is going to end up equaling a -7 times a +3 would be a -21. On this one, I have subtraction, so to get rid of this subtraction, I'm going to add the 1 6/10. I'm going to have to add it to both sides. Okay, so I'm left with x because -1.6 plus 1.6 is 0. And then that is going to end up equaling a -6 8/10. Right? And this part I'm fine if you guys use a calculator on. Here, I'm multiplying because I have my coefficient right next to my variable. So I'm now going to undo that by dividing by 4, and I'm going to divide this side by 4. So I cancel this out and I cancel this out, and then I get x is equal to, and -2 divided by a -4, it's a negative and a negative, is going to give me a +2/4, or if I simplify it, which we need to make sure we're doing, equals a +1/2. So that's the ultimate answer I'm looking for. So as we go through these real world examples, looking at strategies of what we know, what we need to know, and how we can plan out our work is going to help us through these processes. So if a chocolate cake is divided into 6 equal slices, and each slice has 280 calories, how many calories are in the whole cake? All right, so what I know is that one whole cake is equal to 6 slices. I also know that one slice is equal to 280 calories. What I want to know is number of calories in the whole cake. So there's got to be a solution of how I can get there. So if I take my my whole cake and I divide it into 6 slices, I know that each of those individual slices is going to end up with 280 calories. So this is my whole cake, okay? It's divided into 6 slices, and each one of those slices is going to be 280 calories, right? So then my solution, to go about getting my solution, I would go through and solve this. So I'd multiply by 6 and multiply by 6. So X is going to end up equaling 1,880 calories, but the most important thing here is to apply it back. The whole cake has 1,880 calories. All right, the last one that we have here, and this will end up our lesson for today. Pedro made a pot of coffee for some friends. So I'm visualizing this pot of coffee. He served 34 ounces to his friends and then measured that there were 20 ounces left over. How much coffee did Pedro make? So he served 34 ounces and he knew that there were 20 ounces left over. So that's what I know. Served 34 ounces left over, 20 ounces. I want to know how much coffee did he make? So when I think about this, I think about a pot of coffee, okay? This whole pot of coffee, I don't know how much is in there. So we're going to call the pot of coffee X. And as he's going around and serving it, he's serving or getting rid of 34 ounces. And when he's done serving his 34 ounces, he has a total of 20 ounces left over. So that's how I come up with my equation. So in order to solve that, I need to isolate my variable. So I'm going to get rid of this 34, and I'm going to do the opposite of the subtraction. So I'm going to add 34 to both sides. I'm left with 6. Remember, negative 34 plus 34 is going to be 0. And then I'm going to add 20 plus 34, and that is going to give me 54. So my solution is not just 54. My solution is applied back to the answer. Pedro made 54 ounces of coffee. All right, guys. So this is how we bring this into a real-world application, making sure that we're able to solve for that variable. Key takeaways: we need to isolate the variable by doing the opposite of the operation, and you have to do it to both sides to keep it balanced. So make sure you get your good practice in. Do a super good job. If you have questions, feel free to reach out. I'm happy to help.